Yep, welcome. Thank you very much for attending. I'm Tom Davies. I work for WhatsApp, and I've spent a good portion of my time thinking and doing Dialyzer. You may have seen me before. I've given talks about Dialyzer at CodeBeam before, and I'm back with more Dialyzer stuff. This time, I'm going to go down the performance rabbit hole and talk about a whole bunch of things that I learned and tricks that I used to make Dialyzer even faster. These things aren't in the wild yet, but at some point soon, I hope to make it so everyone can make use of this. So as our code base grows, I think it becomes harder and harder for us as individuals to understand what's going on, to spot bugs, so on and so on. We have to rely on our tooling more and more to scale up, to automate the process of finding mistakes, inefficiencies, et cetera, et cetera. And that means also that the tooling needs to be performant enough to actually do that in a reasonable amount of time. And I think it's not unheard of for Dialyzer to take hours to run on very big code bases. So a lot of my focus has been on just trying to make it finish in a reasonable amount of time. So pre-OTP 26, Dialyzer existed with this idea of the persistent lookup table, the PLT file. And the general idea behind that was you had a bunch of code that you were actively working on, like your user-facing product app, and then a bunch of stuff that didn't really change, like OTP itself, or some third-party libraries, or what have you. And so you could stash the stuff that didn't change in the PLT file, and then use that as a kind of a look-aside thing while you analyzed your actual code. So you can see there's some amount of something that sounds like reuse and caching. But then in OTP 26, we worked on incremental Dialyzer. And there, the PLT's semantics changed a little bit. That's where we actually got to the point where you make a small code change in your code base, and then Dialyzer does sort of a commensurately sized analysis, which sounds great. And I think at the time, I was quoted as saying it was 7 times faster in practice for the things that I'd tried out, which was really cool. That really took a big chunk out of our CI time, made local workflows quite a bit more efficient. So yeah, I'm back again with similar tricks up my sleeve with what I'm currently calling Granular Dialyzer. And with incremental Dialyzer, the core unit of incrementality we had was the module. So either, from Dialyzer's perspective, either you changed a module or you hadn't. And therefore, some other modules that depend on it either need to be reanalyzed or they don't. So Granular Dialyzer is about making that not just about modules, but in fact smaller units, like maybe only functions or types. So yeah, that's what I've done with the time that's been given to me. So thinking about the architecture inside Dialyzer to make this possible, the general approach to the problem, in incremental Dialyzer from OTP 26, if you had the string module, and the string module depends on the Unicode module, the Unicode util module, the lists module, that would mean that if you changed, say, the lists module, then you would have to reanalyze the string module because the thing that string module depends on has changed, and so maybe that's changed something inside string. Maybe you changed the definition of a module inside the lists, sorry, of a function inside the lists module, and that means that now the thing that you're doing inside the string module makes no sense. And Dialyzer's only choice was either to reanalyze the whole module or not. So now, with this proposed Granular Dialyzer that I've got a proof of concept working on inside WhatsApp, we now look at the type and function level dependencies. So before, where we had the string module and the lists module and so on, now we look at the string pad function. And that depends on the Unicode char data type, depends on the lists duplicate function. And so we've got much more ability to avoid doing redundant analysis. Now we only need to reanalyze the string pad module, say, if specifically the lists duplicate function has changed, and not just anything inside the lists module. And you can say the same here as for string length or whatever else. You can see that now what was just one big bag of soup is much more granular. And then along those same lines, we considered record deduplication. So quite a common pattern is that you have one header file, and maybe that defines a record, and then you include that header file in several different locations. So this is kind of handy because you don't need to type out a definition in multiple places. You type it out once, and it appears everywhere. The slight complication from Dialyzer's perspective is the way this actually works under the hood is the preprocessor, during compilation, runs over the header file and logically copies and pastes the contents of that header file into each module. So from Dialyzer's perspective, once compilation is completed, if you had in your header file this person record, which had some various fields, now that same record is copied and pasted into all of these places, and you don't have your one record anymore, you have n records. And in fact, in practice, it turns out, after I did a bit of investigation, that this situation can occur even outside of header files being included. That is to say, the same structural record exists in many places, has the same meaning, but it's given different names and defined in different places. So the solution here is essentially to hash the structure of a record. And so if it's semantically the same record, we'll analyze it once and reuse that knowledge all over the place instead of every place it's been copied and pasted, redoing that same work. So as you can imagine, if you have at the core of your business this one header file with a few records that are included in 10,000 other modules, that's like 10,000 times less analysis that Dialyzer needs to do, and that corresponds to quite a good performance boost. So one of the other considerations I had was data representation. So even I'd achieved my original goal. I'd managed to make Dialyzer much more granular, and the performance improved quite a lot. But I was still kind of getting frustrated, even myself, running Dialyzer on our fairly large code base. And I was thinking, surely I can make this better still. So the sort of things I considered were memory footprint, because if you've got a large code base and Dialyzer loads the whole thing into memory, we're talking gigabytes, tens of gigabytes, maybe more, of memory soaked up with just essentially your code. Also considered what operations are efficient for the given data type. So we really want to make the things that Dialyzer does all the time, like comparing types, to be very efficient and not so much worry about things that it doesn't do. And what I've called binary to term sympathy is really about serialization and deserialization. It just happens to be that Dialyzer uses term to binary, the core offering inside the Erlang module. In other cases, it could be anything else, but the point here is really that we wanted a representation for types, which are what get written out into the PLT file, to be efficient even when you'd written it out to a binary. So you wanted something that could be serialized quickly, and something when it's serialized to be quite compact. So one of the decisions to make was lists versus tuples. And on the face of it, it's usually quite a straightforward choice. If you've got a fixed size of thing, then usually use tuples. And if you've got a variable size of thing, you might want to use lists. But in some sense, they both just contain collections of data. And in the case of Dialyzer, often what you're faced with is very small collections of like 10 or 11 elements in situations like unions of types. And in that situation, there's a few different things to consider. So in lists, the representation of an Erlang list is a linked list. So you have an element in a conn cell, which points to the next conn cell that contains an element, which contains a pointer to the next conn cell, and so on. And if you're not careful, the size of that reference can be just as big as the elements inside the list, or the things that they reference. So actually, a lot of your memory overhead is just pointers to the next element in the list, rather than the stuff that you're storing and actually care about. And with these pointers to the next element, there's no guarantee that that region of memory is going to be contiguous. And obviously, modern hardware is kind of optimized for contiguous reads and writes, just in part because that's the simplest thing to do, and part because that's often the way things work. Here, lists don't really work that way, so in practice, you pay a bit of a performance penalty. Now, it's not always the case that things aren't contiguous in memory. It can be that way if you've constructed them very close to each other temporally, that it works out that way, but it's certainly not guaranteed. And also, a lot of the operations on lists are linear. So if you want to find the length or index into a list, you have to traverse the whole list. Thankfully, this is actually very fast in Erlang, but nevertheless, it is linear, so if you have a big enough list, it takes a long amount of time. So that's another sort of consideration, the size of the lists that you'll have. And then structural sharing, if you have a linked list, it's immutable in Erlang, which means you can change the first element, say, of the list, and then reuse the rest in an operation. So that's kind of like a positive feature that we have. And then comparing that to tuples, well, tuples are very compact. In some sense, they're basically just like a C-style array of data. They're just like a contiguous blob of references to the elements. So from that sense, yes, they're very compact. They're also kind of quite amenable to the models that are assumed by lower-level tools and the CPU and so on. And you can do things like find the length and index into it in constant time. One of the main drawbacks is that you usually then need to copy to update them. They're just like a contiguous blob. You need to make a change. OK, well, I'll copy it and then have this little thing tweaked over here. I say usually because it's possible to optimize some of that away, but it's certainly not guaranteed that you'll have that optimization applied. So these are some of the things that I considered when thinking about the representation used inside Dialyzer. And in fact, it turned out in practice, using tuples instead of lists as my container type for small numbers of elements was substantially faster for performing quite a lot of operations. Then thinking about the Erlang term format. So if we use term to binary to serialize what's written to the PLT cache by Dialyzer, there's quite a few gotchas there. And I think actually the documentation for the Erlang term format is excellent, totally comprehensive. But that also means that you've got to sift through a lot of knowledge and then think about it a little bit to come to these conclusions. So this is really from the perspective of me assuming one thing and then finding out something else. So one example is the serialization of atoms. So the nice thing in the Beam at runtime is that each atom isn't really a string. It's just an index into a table that contains that string. And so if you have lots of instances, you've just basically got a bunch of integers that point to a string, very cheap to handle. But as soon as you call term to binary, you don't keep that knowledge of reuse and just an index into a table. You now really do create a string for each one of those cases. And so you get in this weird situation where your code essentially can get faster if you just use shorter atoms. And that means also if you have like record names, function names, if you just make them shorter, Dialyzer would get faster. It's a bit strange. Certainly counterintuitive. Another consideration was that it turns out when you call term to binary, tuples are more compact than lists, kind of like the in-memory representation, apart from there's a bunch of optimizations in the Erlang term format. For example, the empty list is very cheap to store, and also lists specifically of the numbers in the range 0 to 255 that are less than 2 to the power of 16 long are also really compact. So like there's all these strange trade-offs where if you can just find the perfect combination of stuff, everything gets much faster. A slight surprise as well to me is that if you call term to binary on a term that itself contains binaries, like if you call term to binary on a pair, and that pair contains 2 binaries, then that's actually quite expensive because there's this header to say my term is a binary that then needs to be copied around as well. So with all of this in mind, I started poking around inside Dialyzer to make things faster. And as Michał said in his talk about JSON before, you really need to validate this stuff. And here's like a simple way of doing that for term to binary. You call term to binary, you call the byte size function, and just see how big it is. So I'm running very low on time. I'm going to start skipping through. And if you want to know more, because I will inevitably run out of time, come and speak to me, and I'll publish the slides and all of that good stuff. So one of the unintended things I discovered while working on Dialyzer and trying to make it faster is a bunch of micro-optimisations, which in my mind would maybe be done automatically by the compiler and what have you. And it turns out it's all true with some caveats. So inside Erlang, as we've heard about from some other talks, inlining isn't switched on by default because it changes the contents of your stack traces and things like that. And what's more, switching on inlining itself doesn't guarantee that anything's inlined. You also need to set a bunch of parameters like inline effort, inline size, that makes the decision for when something will be inlined versus not. If we just always inlined, then our code would massively bloat, as you'd have millions of copies of the same function inlined everywhere. But even with those things applied, it turned out if by hand you rewrote some of this stuff, you could start to get some really nice performance improvements. So here I have an example of an original, terse, nice-looking drop last function that takes a list and gives you a new list with everything but the last element. And now here's another one on the right, which is unrolled. So instead of operating on one element at a time, I'm operating on ideally 4. And if the list is less, then the amount of elements that are in the list. And what we're really doing here is saving ourselves the cost of a function call. Why call the function recursively 4 times when we could call it just the once? And for list operations, that turns out to make a very big difference, because a lot of what they do really is just calling the function itself again. But you can go a bit further than this. Here we have an example of the list duplicate function, which takes the number of times we want to duplicate an element and the element itself. And similarly, we can check that we're given an integer, the number of times to duplicate, and the element itself, and make sure the number of times is in fact an integer, and it's greater than 0, and then builds our resulting list element by element. But we have a few inefficiencies here. When we recurse into duplicate the second time, we're checking again that it is an integer and n is greater than 0. But you can certainly imagine, if you're looking at this and playing it through in your head, that if we start off with n equals 10, we know it's an integer, we know it's greater than 0, and when we recurse into ourselves, it's still going to be greater than 0, and it will be for a little while yet. So we can take away that knowledge and say, well, we'll make that check just the once at the beginning, and then handle all of the possible cases that arise as a result of that. And so we can do our unrolling here, but we can also handle the guard situation as well and get rid of it when we recurse, because by this point we've ruled out any of the possibilities. And so we don't even need to have the guard at all. I suspect I'm now running out of time. So I'm going to skip my section on ETS performance, and there we go. So Donald Knuth said premature optimization is the root of all evil. And I think the conventional wisdom in software engineering is developer time is worth more than CPU cycles. And I think both of those things are very true. Nevertheless, I've just spoken about hideous things that you can do to make your code faster. So this is my get out of jail free card as a tooling author, which is, well, actually, Dialyzer CPU cycles themselves cost developer time, and so I'm saving developer time by making my code faster, and so all is good in the world. Thank you very much for listening. I welcome questions, and I will share the slides that I didn't get to show you. Thank you very much.
Right, thank you very much. Yeah, maybe we have time for one quick question, if anybody has a question. But we're in a, oh yes.
When looking into atoms in term to binary, did you consider extending the term to binary in the form that it keeps that, like the distribution protocol, the table?
Yes. I can expand on that quite a lot, actually. So term to binary already does what you're describing in sort of the node-to-node communication context, and it's only when serializing to disk that it doesn't, because you don't have the same guarantees of like who you're talking to on the other end of the disk write. Yes, in fact, all of the things that I've discussed, I'm in the process of also trying to make the OTP tooling resolve automatically for you. So there's some thoughts about how to improve the Erlang term format to do what you described. There's some thoughts about applying the loop unrolling and guard optimizations in the core list library and some other places where the performance is really critical. And I'm also thinking about compiler optimization passes and the future of inlining and whether there's something I could contribute to making that all happen automagically. Because the reality is, if you have to unroll these things manually, it's going to look terrible, but sometimes you do need the performance, so why not both? Let's make the tools do it. So yeah, that will probably be the subject of a future talk, but I don't want people in the future to have to do this by hand. And so yes, I'll try and contribute to the tooling to make it just happen.
Thanks.
All right. Thanks again. Round of applause.